podcast is brought to you by LMU Munich.
Thanks very much. So I'm going to give 3 lectures about singularities in string theory. So why do we ever have to consider singularities in string theory? That's the first question. So question number 1 is why? Well, when we study string compactification, as James explained in his lectures very carefully, the solutions we're most familiar with involve Calabi-Yau manifolds. And the way we use Calabi-Yau manifolds to construct string solutions, well, we use some fundamental properties about the metrics of those Calabi-Yau manifolds, namely that there's a covariantly constant spinor. But at least for a compact Calabi-Yau manifold, there's this beautiful theorem of Yau. So this is called Yau's proof of the Calabi conjecture, which tells us that there's a one-to-one correspondence between Ricci flat metrics on a Calabi-Yau manifold and simply Kähler classes on algebraic varieties X with first term class 0. So it's really hard to study Ricci flat metrics in detail. As James mentioned, recently there have emerged techniques for making numerical studies of these metrics, but in general we have very few techniques for uncovering any properties of the metrics other than to invoke this beautiful theorem, which tells us that we can at least understand what the cohomology class of the Kähler form and the complex structure, use those as a sort of labeling of the possible metrics, and we can learn something about the properties of those metrics and the properties of the associated string compactification by invoking this theorem. So on this side, we definitely have differential geometry because we're interested in the metric itself. And on the other side, we have algebraic geometry, in which we study these spaces by using essentially polynomial equations in a number of variables to try to find particular algebraic varieties with this property of having first term class 0. So the problem arises that if you look at the set of all possible Kähler classes plus complex structures, which we're using to label the possible Ricci flat metrics on one of these manifolds. So maybe that's a fixed topology of X, just to fix ideas. This set is an incomplete set. So this set itself will be some kind of configuration space for string compactifications, right? As we heard in some of the lectures, we can identify some of the parameters here as moduli in the effective field theory. We can use the techniques from that effective field theory to put a metric on that moduli space, a 2-point function for the moduli fields in the theory. So there's a natural metric on the set of structures, but it's an incomplete set. And in fact, there are paths to the boundary of finite distance. And that's disturbing if you're trying to study the full set of theories. You somehow would hope that your configuration space that includes all of the possible compactifications would at least have a complete metric on it. So there wouldn't be any paths to the boundary of finite distance. If you had some path of finite distance, when you got to the end of it, you would still have a point in your configuration space. from the point of view of algebraic geometry, this is easy to explain. So algebraic geometry studies these things by considering some set of polynomial equations. So I'll just use vector x to denote a whole bunch of polynomial variables. And if f1 through fk are general, then you get a non-singular space. But if the parameters take special values in those polynomials, you can end up with a singular space. And again, for the non-singular values, you should be able to follow a family of metrics, and then you have some kind of metric singularity. It's a little hard to, because I'm using this indirect way of attacking the metrics, it's a little hard to say what kind of metric singularity I would get, but you would get some kind of metric singularity if you go to the boundary. So algebraic geometry has good techniques for studying this situation, exactly because we can think of the limiting object as still being described by a bunch of polynomial equations in a finite number of variables. And we can attempt to apply those spaces in string theory, but we have to do so somewhat cautiously because we have a less tight connection between the differential geometry that we would like to use and the algebraic geometry. So this is one motivation for considering singularities in string theory. A second point is that singularities are already present in string theory. Well, string theory handles singularities, some singularities well. Actually, I probably shouldn't write that low for the sake of people in the back. Let me go over here. So string theory handles some singularities well. And this is an observation from the early days of string theory. Namely, if I have a space X and I have an action of a finite group, acting on X, I can form the quotient X mod G, and this typically has singularities at fixed points of the group action. Those are called Orbifold singularities, typically. And it was realized in the early days of string theory that this string had an interesting way of dealing with an orbifold singularity. Namely, if I think of a closed string as a path that goes from, as a loop, that starts at one point and ends up at that same point, there's a way to incorporate the orbifold action in a perfectly smooth way. Namely, I can take up on X paths which go from one point X to another point Gx, but are not necessarily closed paths. So I can put in sectors of the string theory which study paths of that kind, connecting points to their images under the group action. And in that way, so these are called twisted sectors. And in that way, I can get a perfectly well-defined notion of what it means to take string theory on a background like this, on a background with orbifold singularities. So on the one hand, we know from this sort of analysis that there have to be singularities. On the other hand, there's at least one class of singularities which are well behaved for string theory. So what I'm going to describe to you is various ways of describing the singularities that can occur from algebraic geometry in general. And at least for the first couple of lectures, most of those singularities are going to be orbifold singularities. In the third lecture, I'll talk about singularities of Calabi-Yau threefolds, and we get well beyond orbifold singularities in that case. There's still, for this reason, a good reason to study them, but maybe we don't have the orbifold techniques available to us to fully understand what's happening in the string theory. So I should mention that the very simplest string compactifications, namely cases where we take X to be a torus, singularities don't occur. So this phenomenon of this being an incomplete set, this I should say unless X is a torus. A lot of the earliest studies of string compactification were studies of toroidal compactification, and so this kind of phenomenon was not encountered. On the other hand, even in those early days, it was realized that you could do this orbifold construction. So people did toroidal orbifolds and sort of had singularities built in from the beginning. Anyway, once people got to more complicated Calabi-Yau manifolds to be used for string compactification, this became an issue right away.
One more question.
Yes?
Are you saying that for every space other than a torus, this is an incomplete set? Or?
I'm saying that I'm not aware of any other Calabi-Yau manifold for which has no degenerations. Can I prove that, or am I just not aware of it? I'm just trying to think. The fact that there are no degenerations in the toroidal compactification, you can actually argue on the basis of maximal supersymmetry for the compactified string theory. So many of the phenomena that we see in these incomplete spaces really have to do with the fact that we have less than maximal supersymmetry. I'll make that point a couple times when I get there. Okay, so let me mention that there are two methods to study singularities in algebraic geometry. And we'll describe both of them and learn how to use them. One is what's called a resolution of singularities. So let's see. What I want to imagine, what I'm going to use as notation is x sub 0 for my singular space. And in a resolution of singularities, I try to replace x sub 0 by something which is closely related to it. So x sub 0 tilde and x sub 0 are going to have the property that the rational functions on x sub 0 tilde and x sub 0 are the same. So I'm not changing the space of rational functions on these spaces. By the way, something which hasn't been emphasized in any of these lectures yet is that the key mathematical feature in algebraic geometry is to look at the algebraically defined functions. So if I've got an algebraic variety defined by a bunch of polynomial equations, then there's a natural class of functions to look at. Of course, it's a complex manifold if I'm looking at over the complex numbers, and I can look at holomorphic objects since it's a complex manifold. But there's another class of functions which is a really interesting one, which is the functions that are a little more globally defined, and those have to be polynomials, or in the case of rational functions, quotients of polynomial functions in the ambient variables. So this collection of rational functions, it's a field of rational functions associated to an algebraic variety, is a very important invariant. And in resolution of singularities, we'll try to find something which doesn't disturb the rational functions. And a way to make that happen is to make sure that there's an open set in each of these guys such that this map, pi restricted to u0 tilde, is an isomorphism. If you think about it, when I'm studying a rational function, I really only care about the behavior of that rational function on open sets. Well, you might have extra poles away from the open set, something of that sort, so you also have to control what kind of poles there might be. But the rational functions are essentially determined by what happens on an open set. And so this is how we'll guarantee that the rational functions stay the same. So we want ways of modifying the original singular variety. And x0 tilde should be non-singular. should be a manifold. So we'll want ways of modifying the original singular variety to become a non-singular variety without changing the rational functions. And the way that we avoid changing the rational functions is by having some open set on which we've done nothing in making this change. So that relates a singular variety to a non-singular variety. We'll see that in string theory, it's natural in many contexts to restrict to certain special kinds of resolution of singularities, if those exist. And then this process of resolving singularities will actually be interpreted as a process of changing the Kähler class on the non-singular space to approach one of these paths at finite distance where there's a singularity emerging. So the things that are sort of smashed by this map will have a size. That size will be measured by the Kähler class, and we can actually imagine turning that map into some continuous family of deformations of the metric on the corresponding space to wind up at x0. The second method for studying singularities is a deformation of singularity. So here I'll imagine taking a larger space, x0, over some parameter space, which I'm often going to call delta. And delta contains points t, and over the point t is some x sub t. So now we should make some hypotheses about such a family. So f should be well behaved in some sense. And I'm not really going to be able in these lectures to go into the technical definitions of what we would want for well-behaved. But what we're imagining is that at different parameter values, t now becomes a parameter. At different parameter values, we have different spaces. So x sub t should be non-singular when t is not equal to 0. Delta is just a disk. This is maybe the set of t in C such that norm of t is less than 1 or something like that. X sub t should be non-singular when t is not equal to 0, and x sub 0 is my original singular space. So this is the situation with the other kind of path to the boundary in finite distance. I was labeling my possible classes of Ricci-flat metrics by a Kähler class and by a complex structure, and I can let either one of those go to the boundary. If I'm letting the Kähler class go to the boundary, I'm undoing a resolution of singularities. I'm blowing down from x0 tilde to x0. If I let the complex structure go to the boundary, I'm doing something like this, taking t to go to 0, where I have non-singular spaces for t non-zero, and then a singularity is acquired at t equals 0. So these two sort of traditional mathematical techniques for understanding singularities model the two different ways that these singularities actually arise when we're thinking about the set of all possible string compactifications. Okay. So it's really okay to get it wet, is that right? That's what I've been told. So the one other thing I want to say in these general remarks has to do with Dbrane solutions. So up here, I've been talking about solutions to string compactification which just used a Calabi-Yau manifold, but we can take more general solutions which use a Calabi-Yau manifold X together with some Dbranes, typically supported on some subvariety, Y and X. Well, there are two basic cases. One case leads to algebraic subvarieties. The other case leads to, in the case of a Calabi-Yau threefold, special Lagrangian subvarieties. I'm not going to talk about that case at all. I'm really going to focus on the case of algebraic subvarieties. And the point is that the metric is now modified. So I still have a metric which is conformally Calabi-Yau, but there's a warp factor associated with approaching the brane. And for most brane solutions, this typically pushes y to be at infinite distance. So if I have a metric in which I've pushed y to be at infinite distance, then possibly I don't care if there was a singularity along y or not. So the idea for making use directly of Calabi-Yau varieties with singularities in string theory is if x is singular, but the singular set of x is completely contained in y, then the brane solution may be okay, simply because I don't really care about a metric right at y. I only care about the metric away from y. And the warp factor is going to push that metric away. So we'll see this kind of phenomenon happen a few times. Let me mention one sort of modification of this idea. So I said that the warp factor pushes y to infinite distance. There's one case in which that doesn't happen. So if we use D7 branes, y is not at infinite distance. And I'll have more to say about that in a bit. Yeah, D3 branes in flat space. So there's an infinite throat with respect to the warped metric used in the supergravity solution. So I start out with a Calabi-Yau metric on x, but now the supergravity solution, the brane solution, has a warping factor. And if you measure distance in that new metric with the warp factor, you discover that there's actually an infinite throat approaching the brane. So typically, we make this model in string theory in which we attach the endpoint of the open string to that brane, and that gives us this mental picture that it's not that far away. But from the supergravity point of view, it actually is infinitely far away. So there's a complete metric on the complement of the brane just in the supergravity solution. Okay, so singularities. Singularities of algebraic varieties are very complicated objects in general. There are lots of them. And to try to organize our thinking about these singularities and how they occur in string theory, I'm using the following strategy. So in lecture 1, that's today, we'll talk about singularities in complex codimension 1. Singular locus is going to be some algebraic set inside of my algebraic variety, and so it makes sense to talk about its codimension. In lecture 2, we'll do singularities in complex codimension 2. And in lecture 3, we'll do singularities in complex codimension 3. Now, having said that, it sounds like these lectures are just going to repeat each other. These are vastly different objects. So here, we're going to learn about F-theory today. Tomorrow, we're going to learn about what are called rational double points. And yeah, just as an advertisement, let me mention that today's discussion starts with some work of Newton, Isaac Newton. Tomorrow's lecture starts with some work of, well, one shouldn't really attribute the things that Euclid wrote about to him. I don't know that he actually did all this stuff, but anyway, his name gets associated to it. And I I don't really know who I'll start with in number 3. Newton, Euclid, I can't really extrapolate back from that too well. So, but the character of the discussions in these 3 lectures will actually be very different. And we really won't get to the place where there's a clear distinction between what happens with the Kähler parameters and the complex structure parameters until lecture 3. So in both lectures 1 and 2, I'm going to go through these 2 general types of approach to the singularity, but particularly tomorrow, it's going to be a little hard to distinguish between the 2 different approaches. And anyway, in the case of codimension 3 singularities, Calabi-Yau threefolds, that distinction is much more clear. So I'm going to start out, as I said, with something that was done by Newton. Newton didn't publish it. It's in his letters. And it was published, I believe, in the 19th century by a guy named Puiseux. So it's called the Newton-Puiseux expansion. And the idea is that I start with f of xy equals 0 in C2. And I want to find out about the structure of this guy. And so what does it look like? I mean, the typical kind of picture is, you know, I might have various little local components, and those local components might individually have singularities, and we would like to somehow replace this, according to philosophy number 1, the resolution of singularities philosophy. We'd like to replace this with a different guy, in which the one with the cusp turned into some nice smooth piece, this one turned into some nice smooth piece, and away from this point, I haven't changed anything. So I want to learn something about the behavior at those points. Those are complex codimension 1 points. The zeros, an isolated 0 of an equation like this. It doesn't have to be in C2. This technique works very nicely in C2. There's another version of this story called local uniformization of singular curves, which works in any codimension, but this one is really explicit. And so I want to do it in an example. I forgot to give the references. Let me give the references. Yeah, maybe I'll just do it here, since I've got some space. So, references for today. I'll have some more references for later lectures. So some of what I'm talking about is in some old Tazi notes of mine. Always helpful to know the number 0411 120. So these are some Tazi notes. The construction I'm about to give is written up very nicely in a book of Kutkovsky about resolution of singularities. Zero four one 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 two zero. Thank you. And let me just say chapter 1. This book gets pretty intense pretty quickly, but chapter 1 is very accessible. And then I'm also going to describe some beautiful work of Milner in a book of his called Singular Points on Complex Hypersurfaces. Okay, that's the references for today. Okay, so I want to do an example of this Puiseux expansion. Well, and at the same time as doing the example, I'll tell you what it's supposed to do. So my example is f of xy equals y to the 4th minus 2x cubed y squared minus 4x to the 5th y plus x to the 6th minus x to the 7th. And I don't have a nice graph of that, I'm sorry to say, but we'll learn something about what the graph looks like as we sort of do it. And the goal is to write y as a function of x. Well, if the picture is something like the one I drew there, there may be multiple ways of doing that. So one of the issues is, are there more than one sort of local branch of this? So there may be multiple solutions. And we'll see that in this case, there actually are multiple solutions. And the other problem is that, of course, there's a singular point, so I really don't expect to be able to write y as a function of x directly. More generally, what I'm actually going to do is write y as a power series in x to the 1 over n. So P will be a power series. And this is kind of the output of the Puiseux expansion. The Newton-Puiseux expansion is a way of solving equations like this as a power series in x to the 1 over n. So how does it go? It proceeds by what's often called the Newton polygon. So I'm going to make a graph of the monomials which occur in this equation. This, by the way, is a little bit related to the Grosvenor basis story that James was telling us yesterday. So I've got y to the 4th, 1, 2, 3, 4. I've got x cubed y squared. That's this point. I've got x to the 5th y. That's this point. I've got x to the 6th, which is here. I've got x to the 7th, which is there. And that's the complete set of monomials occurring in this equation. So the Newton-Puiseux method says, let's start on the y-axis here and find a line with the property that all of the monomials are either on the line or above it to the right. So the line here is this, and sorry, I'm not really cheating. I just had an inaccurate graph. Those 3 points are collinear, and that one's inside it. I didn't draw it too well, but that's really true. You can check. So that kind of shows me some lowest order terms with respect to a particular weighting on the variables. So the lowest order terms that I've just identified are y to the 4th minus 2x cubed y squared and x to the 6th. And indeed, as you can see, that's a weighted homogeneous polynomial. Maybe it's even more clear what its structure is if I write it in this form, y squared minus x cubed quantity squared. So now you can see that if I give y and x appropriate weights, that thing does become weighted homogeneous. And then there's some other terms. I still have minus 4x to the 5th y and minus x to the 7th. So, oh, sorry, I should go over here. So I'm trying to find this kind of expansion with fractional powers, and I'm not quite done yet, but I'm getting there. So now I'll make a change of variables. And this change of variables, from a more abstract point of view, is a weighted blow-up of the ambient space. I'm going to make a change of variables which isn't quite one-to-one, because I'm going to allow some powers in my change of variables. And those powers are tuned to this behavior, y squared minus x cubed. So the change of variables I want to make is to let x be x1 squared, y be x1 cubed, times y1 plus 1. And I've chosen this 1 so that if I plug in x equal 1 and y equal 1, I'll get a 0 of this leading term. So this is chosen. In general, this would be y1 plus c1, and c1 equals 1 because I want 1 comma c1 is a root of this leading term, y squared minus x cubed squared. So that's the rule. And then I pull out a common factor. Yeah, I should have mentioned, I had no common factor of x in my original guy, and if I had a common factor of x, there wouldn't have been anything on the y-axis. So I'm trying to solve for y in terms of x. I should always, at every step, pull out a common factor of x if it's there. That'll be some vertical component in whatever coordinate system I'm using, and that vertical component won't allow a solution like y equal y of x. So a careful statement of the result says there could be some vertical components which look like x equal constant, x equals 0, but aside from that, I'll be able to find parameterized solutions in this Puiseux method. So here I get y1 to the 4th plus 4y1 cubed plus 4y1 squared minus 4x1y1 minus 4x1 minus x1 squared. All I did was substitute this into here and pull out the common factor of x1 to the 12th and multiply out a little bit of stuff. Sorry it was so fast, but you could reproduce it at home if you wanted to. And now I do it again. I look at what monomials I have. So I have y1 to the 4th, y1 cubed, y1 squared. I have x1, y1. I have y1, excuse me, x1, that's an x, and x1 squared. So this time my line is like here, right? That identifies the leading terms. Those leading terms are this one and this one. And again, I'll take x1 to be x2 squared, y1 to be x2 times y2 plus c2. And now I want to choose it so that 1 comma c2 is a root of these leading terms, 4y1 squared minus 4x1. So there are two choices, two possible choices. I could take c2 to be plus or minus 1. Each of those choices I could continue this process with. So I continue the process until I reach the point where there's a y1 in the problem. There are still higher order terms, so I don't actually have the ability to solve for a y1 directly at that point. But if I have a single y1, I can actually find a series solution as an ordinary power series without involving any fractional powers at that point. So once I've got a linear term in y1, there are formal power series solutions that are easy to write down, and I'm done with my fractional exponent business. So it's pretty clear how to turn this into a fractional exponent thing. Here, you know, my y looked like x to the 3 halves, so I actually had something involving x to the 3 halves as the first term in the series. And then, you know, you can re-express the next one in terms of an additional fractional power. You can sort of solve the whole thing for y as a fractional power, and you get various fractional powers appearing. So this is the basic story for resolution of singularities for a curve. The curve will typically have multiple components passing through the singular point. Then for each of those components, there will be some integer n so that the local functions on the curve can all be expressed in terms of x to the 1 over n. That x to the 1 over n is called a uniformizing parameter. So x to the 1 over n is a uniformizing parameter. And it explains what's going on with the singularity of this particular type. Namely, I started out with some coordinate, maybe I'll call it t, and now I've produced an x which looks like t to the n. And what I've done essentially is acted on t by multiplication by an nth root of unity, and the invariants for that group action are formed by the nth power. So t, which is x to the 1 over n, is my uniformizing parameter, and I've made some kind of group identification. So the local singularities in this case local singularity is an orbifold singularity, there's really nothing but orbifold singularities when you're talking in this language about algebraic geometry. And by the way, when there's an orbifold singularity, there's also an orbifold metric. I can just take a non-singular metric upstairs and get something which is a metric away from the singular point downstairs. And that orbifold metric has a deficit angle. I've changed the periodicity conditions so that instead of being periodic with 2 pi, I've got a 2 pi over n periodicity. So if I had a 2 pi periodicity around the edge of my circle, then I would have a metric which, well, on the cone, which behaved well, but since I've got a smaller periodicity, I really get an actual angle at that cone point. And this is the basic type of singularity that you get in complex codimension 1, both metrically and algebraically. So again, it's like taking an angular sector from the original disk and then identifying this edge to this edge that glues it around to literally a kind of ice cream cone type shape with a conical singularity at the origin, measured by exactly that deficit angle. Okay. Yes? C1, absolutely. Yes, thank you. I forgot that there was also a choice for C1. So I get at least 4 branches in this case. Okay, so this is going more slowly than I expected, but that's par for the course. Let me now outline for you the other method, the deformation method of studying singularities. So resolution of singularities is pretty hard when I get beyond complex codimension, singularities of codimension 1, but for codimension 1 it's pretty easy, and this Newton-Puiseux method is the basic thing you have to know. For the deformation theory, so I want to outline for you this work of Milner. So Milner looked in general at singularities that you would get by looking at a hypersurface inside Cn. Sorry, let me do it inside Cn plus 1. And supposing that you had an isolated singular point. By the way, how do we tell if there's a singular point and whether it's isolated? You simply have to look at the partial derivatives. So you look at the common zeros of this, together with f equals 0, and that set should just be the origin. So an isolated singular point. And Milner's idea was to consider the deformation where it's x0 up to xn equals t. So that's the basic deformation. And we'd like to somehow compare the topology of this guy to the original singular fiber. So here's his idea. First of all, I want to restrict my attention to the unit sphere. So I want to take f equals 0, intersect with the set of x's such that the norm of x is equal to 1. You could take a sphere of any radius, but we might as well make it a unit sphere. So if I restrict attention to that, by the way, in this case of C2, f of xy in C2, this set here in C2, when I intersect with the unit sphere, that's a 3-sphere. Each of my branches of the local singularity is going to give me some kind of simple closed curve in the 3-sphere. I get simple closed curves for each of the branches, and there may be different simple closed curves for different branches, and they may actually link each other. So typically, I don't know, I link things better if I prepare in advance. So my chances of linking these are small. Those might be linked and they might not, who knows. You get a bunch of simple closed curves. The curves themselves can be knotted and then they can be linked together if you have more than one component. So that's a sort of typical behavior for f of x equals 0 in C3. And what I'm going to do is take the complement of this. I'm going to take S2n minus 1 minus this intersection. And then on that space, I'm going to use f in a funny way. I'll take f divided by its norm. Well, that's why I had to leave out f equals 0. That wouldn't have made sense. And that gives me a map to S1.